Alright, this is take 3 for me of making this video for you guys, so hopefully you appreciate it. But here we go with position, velocity, and acceleration day 2. So we're doing the same things we were doing before, but now we're going to be analyzing the graph of velocity. And if you remember, velocity is the first derivative of the position function. So that means we're really analyzing the graph of f prime, which we've already done. So now we're just doing it in terms of velocity instead of calling it f prime. All right, so we've got Waldo here. Waldo's pacing back and forth along the x-axis, and this is the graph of his velocity. So we know it's the graph of v of t. He's pondering his clothing choices, his math knowledge, and his ability to blend into a crowd. So the first thing you might be asked to find is his instantaneous velocity. Well, we're given the velocity function, which means in order to find the instantaneous velocity, we just need to look at the y values. So what is Waldo's velocity at time t equals 14? That means just find v of 14. So here's 14, and his velocity then is 3. And we're doing feet per second, because that is our units for velocity. All right. If we want to talk about when he's moving to the right or moving to the left, let's talk about moving to the right first. We know that we're going to be looking for the sign of velocity to be positive. In other words, we're looking for the velocity to be above the x-axis. So when is Waldo moving to the right? It's any place where the velocity is above the x-axis. So from 0 to 3, and then it's positive again from 9 all the way to 19. We're not going to worry about the justifications on here right now. We're going to do that in the next problem. Then if we want to know when Waldo's moving to the left, we know that a particle, or in this case Waldo, is moving to the left anytime the sign of the velocity function is negative. So in other words, the velocity is below the x-axis. So when is Waldo moving to the left? He's moving to the left from, let's see, 3 until 9, and then again from 19 to 20. Okay. Speed, we know that speed is really talking about the absolute value of the velocity function. So if I want to know Waldo's speed at any given point, I'm just going to ignore the sign on the velocity. You can also kind of think about reflecting any negative values over the x-axis. So in other words, we can take all of these negative values and just reflect them up. That's the same as just ignoring the sign, okay? So Waldo's speed at time t equals 5 really means the absolute value of his velocity at 5. So here's 5, his velocity is -3, which means his speed at 5 is just 3 feet per second. If I wanted to know Waldo's acceleration, well, we know that acceleration means that's the derivative of velocity, so we're looking for the slope of the velocity function. So Waldo's acceleration at time t equals 1 means a of 1 That almost looks like a T, sorry, a of 1. So looking at the slope at 1, well, this is a constant slope right here, which is kind of nice because it means then that his acceleration at 1 is just -1, because that's the slope of the line right there. So his acceleration is -1, and the units are feet per second squared. Now this is where it gets a little bit more crazy, all right? If we want to look at where the speed is increasing, first of all, we have to remember that in order to figure out if the speed is increasing or decreasing, we need to look at the acceleration function, so a of t, and the velocity function, v of t. If the acceleration and velocity have the same sign, then we know that the speed is increasing. If acceleration and velocity have opposite signs, then we know that the speed is decreasing. So let's look at the increasing first. So if the velocity is above the x-axis, in other words, if the velocity is positive, and the slope of the velocity is positive, which really means that the acceleration is positive, then we know the function is increasing because velocity and acceleration are both positive. Or a function could be increasing if the velocity is below the x-axis, so it's negative, and the slope of velocity is negative. In other words, the acceleration is negative. So if they're both the same sign, even if they are both negative, it does mean that the speed is increasing. So let's actually look at this on the graph. So if I want the velocity to be above the x-axis and the slope of the velocity to be positive, I'm really looking for anything above the x-axis where the velocity is increasing. So above the x-axis and increasing. Above the x-axis and increasing would be from 9 up to 12. But we also know that speed is increasing if the velocity is below the x-axis, so negative, and the slope of the velocity is negative. In other words, the velocity is decreasing. So now I want to look below the x-axis and be decreasing. So below the x-axis and decreasing happens from 3 to 4, and it happens again from 19 to 20. I know that my intervals are out of order here, but I wanted to do it in the order that we just talked about it because I feel like that makes more sense. So now we did run out of space there. I apologize that there's not a lot of room here. These directions at the bottom actually go on to the next page. They belong on the next page. So we're just going to talk about when we know that speed is decreasing right here. So for speed to be decreasing, we need the acceleration and the velocity to be opposite signs. So if the velocity is above the x-axis, in other words, the velocity is positive, and the slope of the velocity is negative, in other words, the acceleration is negative, then we know the speed is decreasing. Or the other option, and I'm just going to write below these instructions, the other option is that the velocity is below the x-axis, and the slope of velocity is positive. So let's look at the graph and see where this happens. We want the velocity to be positive, so above the x-axis, and we want the slope of velocity to be negative. In other words, we want velocity to be decreasing. So we want positive velocity that's decreasing. Well, positive velocity that's decreasing would be from 0 to 3, and then again from 15 to 17, and then again from 18 to 19. So again, anywhere that it's above the x-axis and decreasing. So that was from 0 to 3, 15 to 17, and 18 to 19. But then we also have to remember we could look for where the velocity is negative but increasing. So velocity negative and increasing would mean we're going from, let's see, that would be 6 to 9. So that is another place where Waldo's speed is decreasing because his velocity is negative but his acceleration is positive. All right, I know that's kind of a lot. There's a lot going on in there. There's a lot of words being thrown at you. So hopefully you guys are still kind of with me. We're going to do one more example and then we're going to save the last one to do together in class so that I can answer any questions you guys may have. All right, so those directions that we just ignored at the bottom of the first page pretty much just told us that this graph is a graph of velocity, which is really important because it means that we're looking at the graph of the first derivative of the position function. So there's a lot going on in this very first problem here. It's asking when the particle is moving forward. Well, moving forward we know means that we want the velocity to be positive, so greater than 0. So we could say that the particle is moving forward on the interval from, let's see where it's positive, from 0 to 30. And we would just say because the velocity is greater than 0. And that's it. We're just looking for where it's above the x-axis. That's nice and simple. Then if we're looking for where it's moving backwards, we should be able to tell that that means the velocity is negative. So the particle is moving backward on the interval from, let's see, 30 to 55. Close that because the velocity, v of t, is negative. It's less than 0. The next part is asking for when does the particle speed up? Well, we just talked about how speeding up means that the sign on the velocity, so the sign on v of t, and acceleration are the same. So we're looking for where either the velocity and acceleration are both positive or the velocity and acceleration are both negative. So the particle is speeding up. Let's take a look here. Well, from 0 to 10, my velocity is positive and increasing. And from 30 to 40, my velocity is negative and decreasing. So I'm looking at those two intervals there. So from 0 to 10 and from 30 to 40. And this one is because velocity and acceleration have the same sign. From 0 to 10, the velocity is positive and the acceleration is positive. And then from 30 to 40, the velocity is negative, it's below the x-axis, and the velocity is decreasing, which means the acceleration is negative. The last part of this question asks for where the particle is slowing down. So slowing down means that we have opposite signs on acceleration and velocity. So the particle is slowing down, let's take a look. Well, from 15 to 30, the velocity is positive, but it's decreasing, which means the acceleration is negative. So the particle is slowing down from 15 to 30. And then let's see. Well, from 40 to 55, the velocity is negative, but the velocity is increasing, which means the acceleration is positive. So from 15 to 30, and then again from 40 to 55, the particle is slowing down because the velocity and acceleration have opposite signs. Sorry, I know there's not a lot of room there. Hopefully you guys are bearing with me there. All right, when is the particle's acceleration positive? Well, we know that acceleration means that we're looking for the slope of velocity. So if I want the slope to be positive, the acceleration is positive anywhere that the velocity is increasing. So from 0 to 10, and then again from 40 to 55. And the justification there is because velocity is increasing. So anytime the velocity is increasing, it means that the acceleration is positive. Which means if I want to know where the acceleration is negative, it means that I need to look for where the velocity is decreasing. So a negative velocity, or I'm sorry, acceleration, acceleration is negative anywhere that the function velocity here is decreasing. So from 15 to 40, acceleration is negative on the interval from 15 to 40 because velocity, v of t, is decreasing. If we want to look at when the acceleration is 0, we're looking really for where the velocity is constant. So the acceleration is 0. Let's see, well, from 10 to 15. And we know that because the velocity, v of t, is constant. All right, moving along here. When does the particle move at its greatest speed? Well, we know that speed is the absolute value of velocity. And we're given the graph of velocity. So we want to look at the highest that the velocity goes, regardless of the sign. Well, this only goes down to negative 40 anyway, so it doesn't really matter. We can see clearly that the highest velocity is right here when it hits 60. So the particle moves at its greatest speed on the interval from 10 to 15. And we're not going to worry about justifying that one. When does the particle reverse directions? Well, it reverses directions anytime it crosses the x-axis. So when we look at our graph here, the only place it crosses the x-axis is at 30. So the particle reverses direction at time t equals 30 minutes. And we're not going to worry about justifying that one right now either. The last one, when approximately is the particle moving at a constant speed? So the particle is moving at a constant speed anywhere that the velocity is not increasing or decreasing. So we actually talked about that here when we said the acceleration is 0, but constant would be from 0 to 15, or I'm sorry, from 10 to 15. So the particle moves at a constant speed on the interval from 10 to 15. Okay, I know that this was a little bit longer. Sorry about that. We are going to do the last example together as a group. All right? Bye.